A Roman merchant ship set sail across the Mediterranean 2,000 years ago. Its destination? Lost to history. Its purpose? Mostly forgotten. But what happened to that ship would go on to help answer questions about our very existence. Sailing off the western coast of Sardinia, something went wrong. The ship sank, sending its crew and cargo to the ocean floor. There, hidden among the ruins, lay over 30 metric tons of lead, 1,000 ingots that would eventually be at the heart of one of the most significant scientific experiments of the 21st century. How did this shipwreck, forgotten for 2 millennia, end up playing a role in answering one of the biggest questions in physics? And how is it helping us understand why the universe exists as it does today? Let's dive in. Our story begins in 1988, when scuba divers off the coast of Sardinia were exploring the seafloor, searching for shipwrecks. They found something extraordinary about 10 kilometers from shore near a small island called Mal de Venter, which ironically translates to stomachache, but is more likely a mistranslation of the Sardinian name, meaning bad winds. Lying 28 meters beneath the waves, the outline of an ancient Roman ship emerged from the sandy seabed. Hidden for centuries, the ship was still recognizable by its remains, particularly the cargo it had been carrying. The wooden structure of the ship had mostly rotted away after 2,000 years underwater, but archaeologists were able to identify it as a Navis Mercatoria Magna, a large Roman merchant ship, measuring about 30 meters long and 9 meters wide, roughly the size of 9 school buses arranged in a grid. The size and design of this ship indicated that it had been built to carry heavy cargo across long distances. The divers weren't just interested in the ship's structure, though. They soon discovered the real treasure, over 1,000 lead ingots stacked in neat rows. The ingots, trapezoidal in shape and about 45 centimeters long, weighed 33 kilograms each. That's about the weight of a large dog or a 10-year-old child. In total, the ship had been carrying more than 30 metric tons of lead. At the time, this was the largest discovery of Roman lead ingots ever made in the Mediterranean, and it was clear that the ship's cargo was one of great value. The ingots were incredibly well preserved, and they even bore inscriptions stamped on the top, telling archaeologists who had manufactured them. Many of the ingots were marked with the names of Marcus and Gaius Pontinellius, Roman citizens who likely ran the mining operation that produced the lead. Some of the inscriptions also mentioned a deceased servant named Philippus, further giving insight into the Roman mining industry. The Romans were big fans of lead. Along with their neighbors, the Greeks, they mined and smelted lead from galena, an ore that also contained silver. Lead was used in everything from coins and anchors to slingshot ammunition and pipes. In fact, lead was so essential that at the height of Roman power, they were producing so much of it that it had left a layer of pollution detectable in Greenland's ice cores thousands of miles away. Lead's durability and resistance to corrosion made it particularly useful for aqueducts and water pipes, some of which are still intact today despite their age. It was also soft and easy to work with, making it a versatile material for the Romans. Though they didn't know about lead poisoning, we now know that lead pipes likely introduced harmful toxins into Roman water supplies, a fact we can't overlook but also can't blame them too much for, since we were using lead in our own pipes not that long ago. But these lead ingots weren't just interesting to archaeologists. While they offered a glimpse into ancient Roman trade and industry, they had a far more important role to play in the modern world, specifically in the world of particle physics. Lead had a unique property that makes it extremely valuable for scientific experiments: its ability to block radiation. Lead is dense and heavy, meaning it's excellent at absorbing or deflecting radiation, which is why it's commonly used in everything from X-ray shielding to nuclear reactors. But modern lead also has a problem. It contains trace amounts of a radioactive isotope called lead-210. This isotope has a half-life of 22 years, meaning any lead that has been mined in the last few hundred years still contains small amounts of radioactivity. For most purposes, this isn't a big deal, but when it comes to high-precision scientific experiments, even the smallest amount of radiation can interfere with results. And that's where the Roman lead from the Mal de Venter shipwreck comes into play. Because the lead ingots from this ship had been processed over 2,000 years ago, all of the radioactive isotopes had long since decayed, leaving the metal completely stable. Furthermore, the ingots had spent 2 millennia at the bottom of the Mediterranean Sea, shielded from cosmic rays that could have introduced new radioactivity. This made the Roman lead perfect for an experiment called CUORE, or Cryogenic Underground Observatory for Rare Events. CUORE is a scientific experiment housed deep beneath the Apennine Mountains in Italy. Its goal? To answer one of the most fundamental questions in physics: why does matter exist? To understand this, we need to go back to the beginning of the universe, about 13.7 billion years ago. At that time, the universe was incredibly hot and dense, and as it expanded, it produced equal amounts of matter and antimatter. But here's the problem. When matter and antimatter come into contact, they annihilate each other, converting into energy. So, by all accounts, the universe shouldn't exist. Everything should have canceled out, leaving nothing behind. Yet, here we are. Somehow there was a tiny imbalance. Just enough matter was left over to form stars, planets, and, well, us. Scientists believe that the answer to this mystery lies with a type of subatomic particle called a neutrino. Neutrinos are incredibly tiny, nearly massless particles that pass through matter without interacting with it. In fact, trillions of neutrinos are passing through your body right now, and you don't even feel them. But despite their abundance, neutrinos are notoriously difficult to study. CUORE aims to detect a rare process called neutrinoless double beta decay. If this process is observed, it would suggest that neutrinos are their own antiparticles, meaning they can exist as both matter and antimatter. This could explain the imbalance that allowed matter to survive and the universe to exist. However, detecting this process is incredibly challenging, as it occurs very rarely, if it happens at all. To detect neutrinoless double beta decay, CUORE needs to create an incredibly sensitive environment that is free from radiation. This means shielding the detectors from any external radiation that could interfere with the results. The lead from the Roman shipwreck was perfect for this task. Physicists from Italy's National Institute of Nuclear Physics approached the archaeologists who had discovered the shipwreck and struck a deal. In exchange for 10% of the lead ingots, the physicists would fund part of the excavation, providing much-needed financial support for the recovery of the ship's artifacts. This agreement wasn't without controversy, as using ancient artifacts for scientific purposes raises ethical questions. However, the archaeologists agreed, recognizing that the lead could play a crucial role in advancing human knowledge. In 2011, the Roman lead was smelted down and reshaped into a 6-centimeter thick shield to surround CUORE's detectors, protecting them from any external radiation. The entire experiment was housed 1.4 kilometers underground, beneath the Apennine Mountains, further shielding it from cosmic rays. CUORE began collecting data in 2017, and while it hasn't yet observed the elusive neutrinoless double beta decay, it has provided valuable information. The experiment has shown that if this decay occurs, it is far rarer than scientists initially thought. In fact, CUORE's findings suggest that the half-life of neutrinoless double beta decay could be as long as 38 trillion years. That's 1,000,000 billion times the current age of the universe. Although CUORE hasn't solved the mystery of why matter exists, it has laid the groundwork for future experiments. The next step is an upgrade to CUORE, called CUPID, CUORE Upgrade with Particle Identification, which will use lithium molybdenum oxide crystals in place of the original tellurium oxide crystals. These new crystals are expected to provide even clearer results, helping scientists inch closer to solving one of the universe's biggest mysteries. The use of ancient Roman lead in CUORE has sparked ongoing debate. While some argue that historical artifacts should be preserved for future generations, others believe that their use in scientific research can lead to breakthroughs that justify their sacrifice. In this case, the Roman lead is being used in one of the most significant experiments in modern physics, an experiment that could change our understanding of the universe. But this isn't the first time that low background materials from historical artifacts have been used in scientific research. Over the years, physicists have sought out ancient lead from various sources, including old church roofs and other shipwrecks. However, this practice can sometimes lead to unethical salvaging and even illegal trade in archaeological materials. As a result, there is a growing need for clear guidelines and regulations on how these materials can be used in scientific experiments. The story of the Maldiventer shipwreck is about more than just a sunken Roman merchant vessel. It's a story that spans 2 millennia, connecting the ancient world with the cutting-edge science of today. The lead ingots that were once destined for Roman coins or water pipes are now shielding one of the most sophisticated scientific experiments ever conducted. As CUORE and its successor, Cupid, continue their search for answers, the legacy of this ancient shipwreck will live on. This is a rare case where archaeology and cosmology collide, revealing that sometimes history holds the key to understanding the universe itself. If you found this story fascinating, make sure to like, subscribe, and turn on notifications so you don't miss any of our future videos. Let us know in the comments, what do you think about the use of ancient artifacts in modern science? Oh, and don't forget to share this video with friends who love both history and space. Until next time, keep exploring the mysteries of the universe.